moment value is equals to, our moment is equals to 0.09 FL, where the F is our design load, our ultimate design load, and the L is our effective span. Now, our ultimate design load F, as we realized from the previous slide, was equals to 21.88 kilonewton per meter, and our effective span is equals to 4.35. So then our moment value becomes 0.09 FL, which is equal to 0.09 multiplied by 4.35 multiplied by 21.88, in which case it gives us a value of 8.56 for our moment at the near middle of end span, 8.56 kilonewton meter. So then the same approach is adopted, and the moment for our near middle of end span has been determined. Our moment at the first interior support also multiplied, we multiply the 0.11 FL by our design loading and our effective span, which gave us a value of 10.47. Then we moved on to the other near middle of end span, also multiplying our design loading by the 0.09 multiplied by our effective span, which gave us another value of 8.56. Now, coming down to our shear analysis, we are being told from the table that at our outer support, our shear value is equals to 0.45 multiplied by our ultimate design loading. So then we pick the coefficient, which is a 0.45, then we multiply it by our design loading, which is 21.88. Now, multiplying it by 21.88 yields us a value of 9.84. That is for the at outer support, or at our outer support. So then at our two outer support at 8 and 6, our shear values are 9.84 and 9.84. Then when we come to our first interior support, which is our support at 7, our shear value is given by 0.6 multiplied by our ultimate design load. Now, 0.6 multiplied by our ultimate design load, which is 21.88, yields us a value of 13.13 kilonewton as our shear force value at that point. So then, having determined our shears and moments in our section, we now move on to determine whether the initial dimensions we give to our section is adequate to resist all the moment and the shear as has been calculated. So again, we revisit our adequacy of section. Now, we should also bear in mind that for the slab that we are designing for, it is a flanged element. Now, as we learned in the unit 1, if you are designing for a flanged element, depending on where the neutral axis would rest, will determine on whether to design the element as a rectangular section element or as a flanged section element. Whether to design it as a rectangular element or as a flanged section element. So then, we now move ahead and determine whether our section should be designed as a flanged element or as a rectangular section element. Now, to determine whether our section is a flanged element or whether to design our section as a flanged element or as a rectangular section element, we'll have to go and calculate for the moment of resistance for a flanged section that has the neutral axis falling along the length of the flange. And that is given by the formula MR being equals to 0.45 FCU DH. 0.45 FCU DHF into brackets D minus HF over 2. Where our FCU is the grade of concrete, our B is our flange width, the HF is the depth of the flange. So then substituting the values into it, we are going to have it to be equals to 0.45 multiplied by a 30 multiplied by 1120 multiplied by the thickness of our flange, which is 150, which is equals to the thickness of our floor slab. Everything multiplied by our D value, which is 357 minus our 150 all over 2. Now, computing this gives us a moment of resistance value of 639.576 kilonewtons meter, which is the moment of resistance for a flange section with the neutral axis falling within the flange. Now, for us to determine whether we are designing for a rectangular section, or we are designing our beam as a rectangular section or a flange section, we should have our moment of resistance being greater than our applied moment, as we saw in our unit 1. When I have my moment of resistance being greater than the applied moment, then it means that my neutral axis falls within the flange, in which case I can design my section as what? As a rectangular element. But then if I have my applied moment being greater than my moment of resistance, then it means that my neutral axis is no more falling within the flange, but then it is falling within the web, and I'd have to design it what? Accordingly. Now, from our previous slide, we realized that our maximum moment had a value of 10.47 kilonewtons, whereas our moment of resistance has a value of 639.576 kilonewton meter. Comparing the two, we realize that our moment of resistance far surpasses that of the applied moment, in which case we can move ahead and say that our neutral axis lies within our flange, and so we can move ahead and design our section as a rectangular section. So all the provisions that we made use of doing our slab design can be applied to this section as well. So then, for our adequacy of section, we can go ahead and say that our K value is equals to our moment divided by our grade of concrete multiplied by our flange width and the square of our effective depth. Now, this is giving us, or this, when we substitute the values into it, gives us 10.47 multiplied by 10 to the power 6. This is because we are converting our moment value from kilonewton meter to newton millimeter, divided by 30 multiplied by 1120 multiplied by 357 squared. This gives us a value of 0.002. Now, again, from the unit 1, we learned that anytime we have a K value which is less than 0.15, it means we are supposed to do a single reinforcement. Whenever we have our K value going beyond or exceeding the value of 0.156, it means that we are supposed to do what? Double reinforcement. So then, coming back and comparing this value to our K prime factor, or our K prime value, which is the 0.156, we realize that our K value, which is 0.02, is less than our K prime value, in which case we can move ahead and design our section as what? As a singly reinforced section. Now, having determined that we are supposed to design our section as a singly reinforced section, we can therefore move ahead and calculate for our area of reinforcement, or as we did for the slab, we can move ahead and design for our moment reinforcement. And in finding the area of reinforcement as we did in the rectangular section for the slab, we saw that the formula for calculating for the area was equal to our moment divided by 0.95 multiplied by our grade of steel multiplied by our lever arm. But then, as stipulated by the DS code, our lever arm should not exceed 0.95 of our effective depth. So we equate our lever arm to what? The 0.95 of our effective depth, and we make use of that provision instead. So then our area of steel now becomes our moment divided by 0.95 Fy multiplied by 0.95 of our effective depth. Now, substituting the values into it gives us our moment value, which is 10.47 multiplied by 10 to the power 6. Again, converting it from the kilonewton meter state to a newton millimeter state, divided by 0.95 multiplied by 250 multiplied by 0.95 multiplied by 357. which gives us a final area of reinforcement of 139.98 millimeters squared. Now, if we go back to our design data, we made mention of the fact that we are going to use 16 mm reinforcement bars in our section. Now, the area of 116 mm reinforcement bar the area of 116 mm diameter bar is approximately equals to 201 millimeters squared. And according to the provisions of the BS code, in providing reinforcement for the tension zone of a beam, not less than 2 reinforcement bar can be provided at that section. So then if I'm providing for tension reinforcement in a beam, I can't place less than 2 reinforcements at that zone. If I pick the area of 116 mm diameter bar, it has an area which far surpasses the area being required for. But because we cannot provide just one reinforcement in our tension zone, we move ahead and make use of 2 16 mm reinforcement bars within our tension zone. So we go on ahead and say that we are providing 2 number 16 mm diameter mild steel bars, and that gives us a total area of 402 millimeters squared. Since 116 mm diameter bar has an area of 201 millimeters squared. Now, the same thing or the same system or the same method is gone through to determine the area of reinforcement for all the moments that were calculated within the section. So then, revisiting our moment values, we realize that we had 3 different moment values: the 8.1, 8.56 for our near middle of end span, the 10.59, and another 8.56. Now, calculating the area of reinforcement required for the other two, realize that we had an approximate area of 106, that is at the near middle of end span, where we had our moment value being equals to 8.56. Now, at the point where we had our moment value being equals to 10.59, our area of reinforcement required for that section was 130. Then again, when we come to the other side where we had our moment value being 8.56, the area of reinforcement required was 106. Now, since we cannot make use of only one reinforcement bar within those sections, for all of these sections we make use of a minimum of 2 reinforcement bars. And by making use of 2 reinforcement bars at that section with a diameter of 16 mm, the area of steel reinforcement being provided at all these sections is equals to 402 millimeters. So then for all these sections, providing an area of 402 means that we are providing 2 number 16 mm diameter bars at those sections. Now, having finished with our moment design, we now move ahead and do our shear design for the beam. Revisiting our shear analysis, we realize that for our shear at our outer support, our shear value at those points was 9.84 kilonewton, and for our first interior support, our shear value at that point was 13.13 kilonewtons. Now, in doing our shear design, we move ahead and pick the maximum shear value to design for our shear reinforcement. So then our shear force has a value of 13.13 kilonewtons. Now, we need to convert the shear force in the beam into shear stresses. This is achieved by dividing the shear force by the breadth and the depth of the web of our beam. So then we have our shear stress value being equals to our shear force value divided by the breadth of our web, or our web width, which is the 250, multiplied by our effective depth, which is the 375. This gives us a shear stress value of 0.147 newtons per millimeter squared. So where we have our shear force value being equals to 13.13, our shear stress value within the beam was equals to 0.147 newtons per millimeter squared. Now, according to the BS code, under no circumstance should the shear stress value in our beam be greater than 0.8 the root of our concrete grade. The root of our concrete grade, which is our FCU, or 5 newtons per millimeter squared, whichever is the lesser. Now calculating for finding the 0.8 root of our FCU gives us 0.8 root of 30, since our grade of concrete is equals to 30. This gives us a value of 4.38 newtons per millimeter squared. Now, because we have the 4.38 newtons per millimeter squared being lesser than the 5 newtons per millimeter squared, our limiting value for our compression shear becomes the 4.38 newtons per millimeter squared. So then, per the provisions of the BS code, under no circumstance are we supposed to let our shear stresses in the beam exceed a value of 4.38 newtons per millimeter squared. Now, comparing our shear stress to our limiting value, we realize that our shear stress falls far below our limiting value, in which case our beam is adequate against compression shear. So then we move ahead and say that since our shear stress value being equals to 0.146 is less than 4.38 newtons per millimeter squared, compressing shear is okay. Now, having found our compression shear, we now move ahead and calculate for the shear capacity of our beam. Now, the formula for the shear capacity for our beam is being displayed on our slide, and that one is equals to 0.79 into bracket 100 multiplied by the area of steel provided divided by the web width and RD effective, or everything raised to the power 1 divided by 3. So then we move ahead and we substitute the values of the formula into it. Now, having substituted the various values into the formula for our shear capacity, we come to realize that our beam section has a shear capacity of 1.52 newtons per millimeter squared. So then, having substituted the values for the various terms in our shear capacity formula into it, our final shear capacity for our beam section is given as 0.530 newtons per millimeter squared. So then our shear capacity now stands at 0.50 newtons per millimeter squared. Now, going back to the provisions of the BS code, the BS code stipulates that now, having substituted the various parameters for our shear capacity into our shear capacity formula, we now move ahead and compute it, and we realize that our shear capacity for the beam is equal to 0.530 newtons per millimeter squared. Now, when revisiting our shear value table in the BS code, the table tells us that if we have our shear capacity, now visiting the table in the BS code, which gives us the provisions for our shear reinforcement, it says that if we have the value of our V, which is our shear stress, being less than 0.5 of our VC throughout the beam, then it means that in the beam of no structural significance, we can omit the reinforcement and the shear reinforcement that we are supposed to provide in. But then once our beam is of a structural significance, then minimum shear reinforcement is supposed to be provided, and the minimum shear reinforcement that is supposed to be provided is given by the formula. Now, going to the provisions in the BS code for our shear reinforcement, it says that if we have our shear stress having a value less than 0.5 of our shear capacity throughout the beam, then it means that in beams of non-structural significance, shear reinforcement can be omitted, and such beams include our lintel beams. But where our beam has structural significance, then minimum shear reinforcement or minimum length are supposed to be provided throughout the full length of the beam, and the minimum length that is supposed to be provided is given by the formula AG being greater than or equals to 0.4 bs divided by 0.87 FYZ, 0.87 FY. So then this area of reinforcement is supposed to be provided throughout the length of the beam as minimum shear reinforcement. So then substituting our values into it, where the B is the breadth of our section or the web width, and the S is the spacing for our reinforcement, the Fy being the grade of reinforcement. We can now move ahead and provide a minimum shear reinforcement of 8 diameter lengths at 200 centers. We can move ahead and provide a minimum shear reinforcement of 8 mm diameter lengths at 200 mm centers. Now, having finished with this one, then we are done with our design for the shear reinforcement and move on to look at deflection in our beam. As we did under the slab design, our deflection in our beam, or our actual deflection, is given by our span to depth value, where our span we realized was equals to 435 and our depth, or effective depth, was equals to 357 millimeters. Now, dividing the 435 by 357 gives us a value of 12.8 millimeters. Now, our allowable deflection is given by 20.8 multiplied by our modification factor. Since all the values given in our span to depth ratio table was arrived at assuming what? A mass concrete element. So once we've introduced reinforcement into our section, we need to factor the effect of the reinforcement on the deflection, hence the modification factor. From our previous study, our modification factor we realized was equal to 0.55 plus 477 minus Fs, all divided by 120 into bracket 0.9 plus m over b d squared, bracket close. Now, our Fs value, as we realized from before, was equal to 2 multiplied by our grade of steel multiplied by the area of reinforcement required divided by 3 multiplied by the area of reinforcement provided. And from the calculations we just went through, substituting the values into it now gives us an Fs value of what? 43.95 newtons per millimeter squared, where we substitute our grade of reinforcement, our area of steel provided, and our area of steel required into it. Now, having found our Fs value, we now move ahead to determine our moment over BDQ value. Now, in determining our moment over BDQ value, we go to the section where we are checking for our deflection, and we pick the moment value at that point. Now, usually our deflections are conducted at the mid span of our beam. So we go to our near end of our mid span, and we pick the moment value at the near end of our mid span. And the moment value at the near end of our mid span was given as 8.56 times 10 to the power 6. We divided by our BD squared, which is 250 multiplied by 357 squared. And that gives us a value of 0.27. So then having determined our Fs value and our M over BDQ value, we can now move ahead and substitute everything into our modification factor equation. And this gives us a value of 0.55 plus 3.08 with an ultimate modification factor value of 3.36. But just as we realized while we were doing the slab design, under no circumstance should our modification factor go beyond the value of 2. But then it seems our modification factor that we've calculated for exceeds. Under no circumstance should we have our modification value exceeding 2.0. But from the analysis we just went through, our modification factor has a value of 3.36, under which case we are supposed to drop the 3.36 that we have calculated for and make do with the 2.0, which is being provided by the BS code. So then, making use of the 2.0 modification factor, our allowable deflection now stands at 20.8 multiplied by 2.0, which gives us a limiting value of 41.6 millimeters. So which gives us a value of 41.6. Now, comparing the 41.6 to our actual deflection, we come to realize that our actual deflection, which was 12.18, is less than our allowable deflection, which is 41.6. Under which case we can say that our deflection check is okay. Having finished with our deflection check, we'll now move on to do our crack check for our beam. And the provision given by our BS code states that the clear spacing between the reinforcement of our beams should be less than or equal to 447,000 divided by our Fs. And that one should also be less than 300. So that if we take the clear spacing of our beam, if we go back and look at the beam that we've just reinforced, The total width of our web, as we saw earlier on, is equal to 250 millimeters. Now, taken from the sides, the distance from the extreme side of the beam to the face of our reinforcement becomes our concrete cover. And as we saw earlier on, our concrete cover had a value of 25. So we have 25 to the sides. Now, we also made use of reinforcement with diameters of 20 mm. So our reinforcement also has diameters of 20 mm, 20 to the side and 20 to the side. Meaning that for the space in between the faces of our reinforcement, which becomes our clear spacing, it becomes the 250 less the 25, 20, 20 and 25, in which case our clear spacing becomes 250 minus twice of 20 plus 25. This gives us 250 minus 20 plus 25 will give us 45. Multiplied by 2 is a 90. So 250 minus a 90 would give us 160 mm. And per the provisions in the code, that value should be less than 300. Now, once I have my clear distance, my clear spacing of my reinforcement being less than 300, it therefore informs me that the amount of cracks that might occur in my beam section is going to be minimal. So then I don't need to move ahead and do any advanced crack check on my beam, in which case my crack check is okay. So then I can now move ahead and do my reinforcement detailings. So that in doing our reinforcement detailing, this becomes a sectional plan through our beam. Then our reinforcement since the same amount of reinforcement we provided at all the sections, I have my reinforcement running through from one end all the way to the other end. With this here as my shear reinforcement. Which is being spaced, my 8 mm length reinforcement, which is being spaced at 200 centers. So then in a nutshell, this is how my reinforced beam after the design would look like. Now applying this to all the beam sections in the building will yield us with a reinforcement schedule as being displayed on the board. And this is the set of drawings that would have to be sent to the site for construction. So having come out with a plan section view, we now take a cross section through the beam and show how the cross section will also look like. So then these are the details that would ultimately have to be sent to the construction site for construction. So having equitably come out with your details from the analysis as has been sketched out on the board, then you are actually done with the floor beam. So then these are the details that would have to be sent to the site for construction and not the calculation that we would have gone through before. So then having come to this point whereby all the calculations has been transferred into equitable drawing, then one can say that he or she has finished designing the floor slab as we set out to do. So then this brings us to the end of our beam design. Thank you very much.